Group 2A presents for your personal delight and educational support the answer to Tutorial 5, Question 1. In Question 1 you are presented with an open fin-walled cross-section which is eccentrically loaded. You are required to produce the bending stress diagram at the fixed support. You will also need to draw the shear flow diagram. For these you will need to calculate the shear force, bending moment, second moment of area and use engineering bending theory. You also need to calculate the maximum shear stress caused by the shear force and torsion. You will need to comment on the relative effects of the shear flow and torsion moment on this value.
So the very first step, we sketch the channel section, and also we use the centerline approximation in our calculation. We also define the x1 and x2 axis. We assume the origin is at the center of the web. Because we need the second moment of area in further calculation, so we calculate the second moment first. We start off with calculating I11 dash equal to sum of the I11 plus sum of the area times the x2 bar square. And this is from in the formula book. We plug in the data for figure 1. We find out that I11 dash equal 191.4 times 10 to the 6 in millimeters to the fourth. Because the channel section is monosymmetric, so we assume I12 dash equals 0. So, therefore, the total second moment of area, I11, equal 191.4 times 10 to the 6th in millimeter to the 4th.
The next step is to produce shear force diagram, which is illustrated on figure 2. Shear force is equal to 10 kilonewtons. To obtain the bending moment diagram, we need to calculate maximum bending moment. Since the beam is in equilibrium, therefore the total moment must be equal 0, and we get force of 10 kilonewtons times the distance from the fixed end to the point at which the force acts, which is 10 meters. But that gives us a moment of 100 kilonewton meters. Figure 3 illustrates the bending moment diagram. It goes from the fixed end along x3 axis to the free end.
To get sigma 33, we use a formula shown, and we plug in the values we calculated for the moment. The x2 value is the vertical distance from the center line of the top flange to the origin. Note that we have converted everything into Newton millimeters by multiplying by 10 to the power of 6. And we get a value of, for sigma 33 of 78.37 Newton per millimeter squared. To get the bending stress diagram, we substitute coordinates x1, x2 on our formula for the edges of our cross-section, and we get the bending stress diagram shown. The top of the beam is in tension and the bottom of the beam is in compression. The convention for tension is that it's positive, and for compression is that it's negative.
Now, for this next part of the question, we need to calculate elements we're going to need for the shear flow. If we look at the situation we're given, we have a point load of 10 kilonewtons that's acting along a vertical axis that doesn't run through the shear center C. It runs somewhere along the top flange. This point load can be considered eccentric, and we want to translate it into a point load that is acting at the shear center C. Now to do that, we're going to create a force that is acting through the shear center C that has the same magnitude as the force, but to compensate, we're also going to include a clockwise moment about the shear center C. To better understand this, here is a diagram. Now, as you can see in this three-step diagram, we are going from a single eccentric force to a force acting at the shear center and a moment. And we're doing that by using the theory of couples. Now, if you look closely at the second step in the diagram, you'll notice that the two red forces are equal in magnitude and opposite in direction, therefore they cancel each other out effectively. You'll also notice that they have the same magnitude as the blue force. So if you take the bottom red force and the blue force and you put them together, you see they form a couple, and that couple is at the origin of the moment you see in green in the third step. Therefore we've successfully transformed our eccentric point load into a point load at the shear center C, and to compensate, we have a moment. With this information, we can now calculate the elements of shear flow in both the flange and the web, starting with the flange. First of all, we're going to need the first moment of area, Q of S, which is effectively the area times the distance x2. Now you notice that they are both dependent on S, which is the axis shown in the diagram, which is figure 1. Plugging in values that we know of and the value for x2, which is halfway along the web, you will get a value of Q of S of 2,250 S millimeters cubed. Now we also know that the shear flow is equal, as shown in this formula, to the first moment of area times the point load divided by the second moment of area. Now effectively, if you plug in with the values we've already calculated, we are going to get a value for the shear flow in terms of S, which is what you have at the bottom here. Effectively, the shear flow in the flange is equal to 0.1176 S newtons per millimeter. Now that we have an equation that allows us to find the shear flow in the flange in terms of S, we need to find a value of S, and we need to find that value so that the shear in the flange is maximum. Now that value for S is 200, and it's the length, effectively, of the flange. Plugging in these values, we get a value for the maximum shear flow in the flange of 23.53 newtons per millimeter.
Now we're going to calculate the shear flow in the web. In order to do that, we're going to use the following formula. The shear flow in the web is equal to the maximum shear flow in the flange plus the contribution for the shear flow in the web, which is expressed in terms of the axis Z. We can now plug in our values and get a complete expression for the shear flow in the web in terms of Z. Now, by using the equation for shear flow in the web in terms of Z, we can calculate the maximum shear flow in the web. In order to do that, we have to pick a value for Z which maximizes the shear flow in the web, and that value is at the midpoint of the web, which means that Z should be equal to 150 millimeters. Hence, we're going to get a value for the maximum shear flow in the web, which is equal to 38.25 Newton per millimeter. We can now plot our shear flow diagram by using the formulas we have in terms of S and Z we've already found before. In the flanges, the shear flow varies linearly, and it's zero at the free end and has a maximum value where the flange meets with the web, which is equal to 23.53 newtons per millimeter. In the web, the shear flow varies quadratically, having a maximum value at the midpoint of the web, which is equal to 38.25 newtons per millimeter. In figure 6, we also illustrate the shear forces FF and FW.
The next step, we find a shear center. We have the formula in the formula book, which we rearrange to find the value of C. To find the value of C, we need FF, which is equal to the integral of shear flow along the flange, as per figure 1. We notice that the integral is the area of a triangle, so we simplify the calculation. At the end, we find out FF equal to 2.353 kilonewtons.
In order to calculate the lever arm, we first calculate the distance of the shear center from the center line of the web horizontally. To do that, we plug in the values for our vertical load, which is 10 kilonewtons, and the length of the web, which is 300 millimeters in our formula, and we get the value for C, which is 70.6 millimeters. To get the lever arm, we add our value for C to the value for the horizontal distance between the line of action of the force and the origin. That gives us a value for the lever arm of 170.6 millimeters. We put everything on our diagram and the point C is the shear center.
For step 10, we're going to look at the last part of the question, which is asking us to report the maximum shear stress present due to shear force and due to torsion. We can start by calculating torsion, which is the force V2 acting at the top of a channel section, multiplied by the lever arm E we just calculated, giving us a value of 1.706 times 10 to the 6 newtons per millimeter. To calculate maximum shear stress, we need to split the channel up into 3 sections. We've got the 2 flanges, we've called section 1 and section 3, and the web, which we've called section 2, where B denotes the breadth and T denotes the thickness. To calculate shear stress tau due to torsion, which we have called tau subscript T, we use this formula, as derived in lectures, where capital T is our torsional moment, T max is our thickness, and J is the torsion constant, which is proportional to the torsional stiffness. So J can be approximated for our open channel section using this formula here, where B denotes breadth and T denotes thickness. It's important to note that the maximum shear stress, tau T max, is only maximum for torsion and not for the total shear stress, tau max. So we start with calculating J for the entire section, which is a third multiplied by the breadth and the thickness of the flange, 215, and then adding that to the breadth and the thickness of the web, which is 325 cube, and then adding that to the bottom part of the flange, giving us a total of 2.0125 times 10 to the 6 millimeter 4. Having obtained a value for J, we can now go on to calculate the shear stress due to torsion, which is calculated separately for the web and the flange. We simply substitute in our values into this formula, where T is 1.706 times 10 to the 6, and J is 2.0125 times 10 to the 6. 25 is our thickness in the web, and for the flange, we've got 15. Now the results we get here are counterintuitive, because we know for shear flow that as thickness increases, shear stress decreases. But for torsion, we can see that as our thickness decreases, our shear stress also decreases. We can now go on to look at shear stress due to bending. We know that this is found by dividing shear flow by the thickness, and we can simply sub in our earlier obtained values for Q and T to obtain these values here. Again, this is done separately for the web and the flange. Finally, we can now calculate total shear stress by adding shear stress due to torsion to shear stress due to bending, giving us 22.72 in the web and 14.29 newtons per millimeter squared in the flange. We choose the larger of those two values, allowing us to finally obtain our maximum shear stress as 22.72 newtons per millimeter squared acting in the web. We can see that shear stress caused by torsion is much larger than shear caused by bending. Therefore, torsion is more likely to cause the most damage and be the mode of failure of the beam, as it could lead to buckling. But this doesn't mean that shear stress due to bending can be neglected, as they both need to be taken into account during the design process.
Group 2A would like to thank you so very much for your attention and sincerely hope that this has contributed to your understanding. Thank you.